So far we have discussed generating discrete and continuous random deviates from a sequence of IID uniform random numbers, but these were all mutually independent. But we will have situations where a problem is defined by several random variables and some or all of them may be mutually dependent. So we need to generate samples of such dependent deviates. We still have a sequence of IID uniform deviates that the computer generates, so we somehow need to use them along with the joint probability information, the dependence information, to obtain the dependent samples that we need. So we'll look at a few cases. The first one is when we have the full dependent structures. We have the complete joint distribution known. So let's take two random variables x and y which are dependent. We know their joint CDF, we know their marginal CDFs, fx and fy, but most importantly we know their conditional CDF. So fy given x or fx given y. So this would be the scheme that we generate u1 from the uniform distribution. For that u1 we invert the CDF of x to get one value of x, and then we generate another uniform u2 which is independent of u1, of course, but then we use that in the conditional CDF of y given x, the x that we just generated in the previous step, and invert that to obtain the deviate y. So this way we preserve the dependence information while making use of the IID uniform sequence. It can easily be generalized to n dimensions. Start with x1, then use that to generate x2, and then use x1 and x2 generate x3, and so on until we have completed the entire n random variables in the n-dimensional problem. So let's walk through an example. This problem we have seen before, we have looked at it twice. This was the joint distribution of h and t, wave height and wave period, and we actually one of the problems we solved was we calculated analytically the probability that h plus t is less than 10. So the probability content over the region defined by the red line and the triangle that contains the origin. So we found that probability is 0.270. Now our task is to do the same thing, estimate the same probability, but this time using Monte Carlo simulations. So let's walk through the steps. The first thing is to be able to generate h. So we need the distribution, the marginal CDF of h, which we get by integrating the density of h, which we get from the joint density of h and t by integrating out t. So we have the ability to generate h, and then for that given h we need the conditional CDF of t. So what we do is that we find the conditional PDF, the density function of t given h, which would be the ratio of fh comma t and fh, and then once we have that conditional density, we integrate that with respect to t, so to get the conditional distribution function of t, and you see both those functions on the screen, and then we can write a small code. So this is what we have. We go through the loop I 1 through nmct, and for each such run through the loop, we generate H from its CDF using RAND, which is one uniform deviate, and then use that value of H to generate the corresponding value of T, its pair, by using another random deviate, and keep doing this, and every time to see to find out if H plus T is less than 10 or not. So if it is, then we increase a counter, which is sum, by 1, and once we are out of the loop, then the probability of H plus T less than 10, or which we soon will call reliability, would be the ratio of the counter over the total number of trials. And if we do it enough number of times, we actually should be able to come close to the answer that we already know. And what you see here is such an exercise. So with increasing number of samples, we see that the estimated reliability does indeed converge somewhere like 0.27.